So to get us started, I'm Carly Anderson, chemical engineer and partner here at Prime Movers Lab. I'd like to start off by welcoming our audience, our limited partners, our founders, our extended Prime Movers Lab family, and a special welcome to our new growth fund LPs who are joining us today. For anyone who's brand new to Prime Movers Lab, we're a deep tech venture firm investing in breakthrough science companies that have the potential to transform billions of lives. This means that we are investing in the foundations of civilization. So things like human health span, agriculture, manufacturing, transportation, infrastructure, and of course, energy. Yay! Today's topic is something that I think is particularly important, yet often misunderstood. As some of you know, my first job out of college was working in and designing technologies for nuclear power plants. And as the transition to low carbon energy has picked up steam, I've been surprised that there hasn't been more talk about nuclear power as a source of firm low carbon energy. Despite the fact that there are a growing number of private sector companies doing really crazy, awesome things in this space, many of whom we've had the potential to get to know, which has been wonderful. So today we've brought together a group of outstanding experts in the nuclear space to share their knowledge of where we stand, where things are headed, highlight some of the important work being done by different groups, companies, agencies, governments in the sector, and hopefully help us answer this question: is nuclear now climate tech? So I'll turn it over to you, G.
Thank you. I'm Gaetano Crupi. I'm a partner at Prime Movers Lab as well. Prior to joining Prime Movers Lab, I was a 3-time entrepreneur and founder. And I had the privilege to be a Prime Movers portfolio CEO with my last company prior to becoming an investor. Before we dig in, a few pieces of information. Our webinar series happens every 2 weeks at the same time. We will keep this to an hour and we try to be very punctual. Please use the chat or Q&A feature to ask questions. As the conversation unfolds, we'll pepper questions that are on topic, but we will also save some time at the end for questions. And I think we have assembled a really great panel to talk about, is nuclear fission part of the conversation when it comes to decarbonization? So what I'd love to do is to start with a very quick round of introductions to our panel, and then we can get right in. So why don't we start with, we have 2 Kristines, so I'm going to go with Kristine King to kick us off on introductions.
All right, thank you so very much. So one, I'm just really glad to see that we are having this conversation. I can definitively answer the question yes, but let's dig into that. I'm the director for the Gateway for Accelerated Innovation in Nuclear. We are an initiative out of the Department of Energy. We get up every day to think about how we commercialize innovative technologies for nuclear energy. As such, I spend a fair amount of my time focused on the public-private partnership. Prior to this, I spent 25 years with today's fleet of nuclear power plants, doing everything from maintenance work to research. So thanks for the invitation, glad to be here. We'll go to the other Kristine.
Okay,
Kristine,
very
yes.
good.
For jumping in and volunteering people.
Okay, I like that. All right, well, I'm Kristine Svinicki. I'm also really thrilled that we're having the discussion and to be here with 2 colleagues well known to me, who I think very highly of. So I'm looking forward to our back and forth discussion and learning a lot from them. But I am currently adjunct faculty at the University of Michigan in the Department of Nuclear Engineering and Radiological Sciences. But most recently, I was chairman of the U.S. Nuclear Regulatory Commission after spending about a decade there under political appointments with Presidents Trump, Obama, and Bush. So I had some deep connection with the regulatory system for nuclear. Prior to that, I spent, again, another decade as an advisor in the US Senate as staff there on topics ranging from national security to energy to environmental law. And prior to that, given my training as a nuclear engineer, my background in that, I began with the US Department of Energy, both at the Idaho National Laboratory and here in Washington, on technology programs, a little bit of a focus on waste, I think would be fair to say, but looking forward to the discussion. And, you know, if we're all gonna have a little show and tell, I will say I'm a yes on the question as well, that nuclear fission is clean tech and climate tech, but it's not a matter of dogma. I think technologies earn their way into the schema, so we can talk more about that later. And I will now tap on the shoulder my colleague, Ben Reinke.
Thank you. Yeah, I'll just go ahead and say yes is the answer in short to question two. So if anybody wants to go ahead and tune out, now is the time. We've already covered all that we needed to talk about today. No, in all seriousness, this should be a really fun discussion. I am currently the Senior Director of Corporate Strategy at X Energy, one of those crazy companies that is commercializing an advanced nuclear reactor technology.
Crazy was the wrong word. I messed that one up already.
No, it's good.
Good
It's a crazy idea, but it's also not. We can get into that a little bit later in the conversation too. But most recently, before this, I was the Executive Director of the Office of Policy and the Senior Policy Advisor to the Secretary of Energy. And before that, I spent about 3.5 years on the Senate's Energy Committee working on nuclear policy. I came to DC after completing a PhD in nuclear engineering. So I'm a tech engineer, nuclear person as well, and then came out here and followed the path a bit of my colleagues as well on trying to get involved in some of the higher level discussions around nuclear here in Washington, DC. So that's me in a nutshell. Thanks.
Okay, well, that just, I'm blown away already, but maybe we can start off by kind of setting the stage for some of the people on this call who haven't spent their entire careers in nuclear, and maybe start around what have we learned from the past? And some might have the perception that nuclear has stalled or not taken off in the U.S. How would you describe, where we're at and what's happened in the last couple of decades of nuclear experience, at least in our country? Maybe Ben, do you mind stepping up again?
Yeah, sure. So I'll give you my 2-minute version of the history of nuclear in the U.S. and why we are where we are today, which is both a really positive story and then a bit of a negative story. And so in a nutshell, the first nuclear reactor operated under the University of Chicago football stadium when UC gave up on playing football because they weren't particularly good at it. Hadn't been around that long. And I think the Rockefellers were still in charge of everything out there. And there was a guy named Enrico Fermi who had come over from Italy, a Nobel laureate who was part of the mass movement of folks away from Europe during fascism and the takeover of both Mussolini and Hitler. And he came to the US and he began working on this crazy idea with Leo Szilard and several other folks of trying to sustain a chain reaction in nuclear fission. So they dug this thing out, built a first reactor pile, as they called it, in what was a squash court because they needed a place that was safe enough to do this and kind of away from prying eyes. And that was really the beginning of the Manhattan Project that launched nuclear in the United States. And in that process, we learned how to sustain chain reactions, and we came up with the beginning origin science of nuclear reactors. Okay, fast forward from there, end of World War II, and the US program is at a crossroads. We can look at all kinds of crazy designs that people have looked at on paper. Later, many of those tested out at the Idaho National Laboratory, where Kristine King works today. And those were all really neat designs, and they had their own benefits and drawbacks. But in order to accelerate and choose a technology, we picked the one that made the most sense for use in naval nuclear propulsion. So that's use in submarines to stay under the water for a long period of time without having to refuel diesel or suck down diesel fumes if you're on board the ship, or eventually to power aircraft carriers, which is pretty cool. And so we chose what was called the light water reactor technology, and that became the basis of the nuclear industry in the United States. And the positive story from there is we really went gangbusters with building reactors for several decades. The United States led the way in the development of light water reactor technology and testing all of these other more exotic different types of designs that you're going to hear more about today. And when we got through that development phase, the US had ramped up to somewhere in the order of 20-ish% of electric power generated from nuclear. We had, at that point, over 100 reactors operating in the United States. And now the last part of that really positive story is that we were continuing to operate those reactors extremely well for an extended period of time, which meant that even though power needs in the United States continued to ratchet up, and we used more and more power in the US through the 1990s, when we didn't build any new reactors, we continued to maintain 20% nuclear power because we got really, really good at operating these safely. That's sort of the long pro story on nuclear. The challenge was that nuclear engineers are engineers, and they like to tinker, and they like to make things better and continuously improve. And it's something that is a challenge for all people in the engineering world. So what we did was we continued to make reactors better. Each one that was built was a little different than a previous reactor. They were mostly customized based on the site and improvements that have been developed over the recent time period before. And at some point in time, after new regulations, a decrease in power needs in the United States, different driving cost factors, nuclear just became a little too costly to continue to deploy at the rate it had been deployed before. And we weren't seeing the types of gains you might expect in deploying a technology in a repetitive fashion. So jump to other areas of the world. The Russians continued to deploy reactors and standardize things. The Koreans have done better than anybody else in the world in deploying a single reactor over and over again and driving the cost down rapidly. So they continue to deploy reactors around the world, and most recently have had great success in their most advanced reactor being deployed in the UAE at what's called the Baraka plant. China has jumped into the game full bore, and they've utilized technologies, many derived from US technologies, French technologies, and others. The French were incredibly successful at building a number of standardized reactors. And again, they had the same issue the United States did, except France actually went all the way up to 80% of their power generated from nuclear power, which allowed them to be the leading exporter of power in Europe. And today, I think they just regained that title again recently. They continue to export nuclear power to Germany and others to provide clean baseload power in the region. But the French haven't been building many reactors in France because their reactors are continuing to operate quite well, and they haven't had issues. So that leads us to today. I will pass it over to my colleagues, but what you're talking about today is a time period where we haven't built a new nuclear reactor from scratch in 30 years because things went well, and then they didn't in the US. And what we're looking at are a number of new technologies that are smaller, more dynamic in their capabilities. They operate in more inherently safe ways, and they're hopefully going to be deployed rapidly and in standardized fashion to drive down the cost of those reactors. And a lot has happened in the last 5 to 10 years, both on the technology development and testing side and on the public policy side. And now I think because of this conversation, it's indicative of what's going on in the capital finance world as well. So with that, Kristine or Kristine, would anybody else like to jump in on what's really been happening?
I'd like to jump in on just a quick point, because Ben, that was a great history and you covered a lot, but for folks who aren't so up close to it, something that could be missed in Ben's narrative is this discussion about the United States looking at a lot of different reactor types, a lot of different what they call fuel cycles. And it's all ways of harnessing the atom and splitting it so it is nuclear fission. But Ben mentioned the fact that the US decided to continue and narrow down that competitive field of technologies to light water reactor technologies. And it was driven strongly. It's hard to overemphasize how much the US nuclear Navy and optimizing around their needs for something that's kind of tunable and drivable like a car because you're using it for propulsion. That one choice and the departure and the pivoting away from the other fuel cycles, which are being looked at now by many really innovative companies in the US, that altered not just the US program permanently, but the nuclear power programs you see around the world, because the US was the domain leader. And so you saw this tremendous competitive edge to light water reactor technology, which as a technology person, I would posit for you, was not necessarily superior for the uses. I was recently watching archival structured interviews with early nuclear researchers in the US. They weren't the people, some of them were at the Chicago pile that Ben was talking about, but they were very junior technicians. Sadly, many of the preeminent names, of course, are no longer with us, but their experiences were really telling, and they were excited about harnessing the atom in these other ways that are now being looked at afresh. They were interested in that because they saw, now I'm going to put my former regulator hat on, some of those fuel cycles and the way that you would harness the nuclear energy and create power from it were so much inherently safer than the large light water technology that we've arrived at now. As Ben said, we harness that safely. We're still operating in this country, almost 100 very large power reactors, but it requires a lot of ancillary complexity in the engineering of the system and a lot of additional safety components. The innovators in nuclear that I've talked to, and I've met with many, as has the other Kristine King, and Ben. They want to simplify the question, and they want to take a technology and a science that initially evolved a very long time ago. They're dusting off some of that early experimental work, and they're putting these new ideas through the fine mesh of both all the computational tools we have now, the way that we develop and deploy technologies, the way we demonstrate things, new engineering, digital engineering techniques. So I often have told folks in the policy space that this relook at technologies that were thought of a long time ago is so fundamentally different. I mean, imagine trying to develop a technology in the 1940s. Imagine all you would have at your disposal in order to develop it now, analytically, computationally. So it isn't just for variety's sake that new technology innovators in nuclear are looking at these things genuinely had a technological promise that the US, in selecting a different technology, kind of left on the drawing board. And there was even somewhat of an arbitrary aspect to it. So I think it's important because you say, why are you reviving it? Why now? Why are you kind of dusting off, at least in a figurative sense, these laboratory notebooks of people who worked in the 1960s? Because the phenomenology, it's radiological process, chemistry, physics, those things have not changed, but you can harness it for power production, for desalination, all kinds of things. And the way that you would harness the atom to do that, fundamentally, it makes sense to me that would be different than from driving a submarine through the ocean. And
so
I don't
Kristine,
know.
Jumping in. First of all, I think what you just said around the improvements in processing power, that's a theme that we see across a lot of industries in terms of the cost structure. And how much better we're getting at modeling and simulating things digitally before we build something. And part of what both you and Ben talked about was the fact that these light water reactors were very complicated. And the United States never built a lot of the same kind. They didn't go through that engineering cost curve. So I'm going to kick it over to Kristine K to talk a little bit about just the cost structure of nuclear and what happened in the late 70s and 80s. Because we didn't make them cheaper, the plants. They got more expensive sometimes. And that obviously is not a good thing when you're trying to scale technology. So understanding that cost structure and how we did that, I think is really important to talk about why it's going to be different this time, hopefully.
Yeah, and I think if you actually look at the way the French deployed their fleet, you see where they actually benefit today from the fact that they have a lot of normalization across their fleet, and they're able to watch their older plants to manage the younger plants coming along, which is, anybody that has done any work in materials degradation, Carly, that's what you want. You want, quote unquote, the canary in the coal mine. We missed that opportunity. We missed that opportunity to collaborate with one another as well throughout this long-term asset that you're building. I mean, the reality is we licensed them originally for 40 years, but right now we're extending those licenses for the existing fleet to 80 years. So we need to think about what we're building here is a 100-year investment. And if we're going to manage a new fleet and a 100-year investment, what are the right choices associated with doing that? And there is that aspect of building an industry together and normalizing. And I think it's an opportunity for us to look at some of the normalization that has happened in digital space. Other industries have learned this lesson already. And I think the opportunity is for nuclear to learn that lesson as well. You don't have to compete on every aspect of the design to be successful at the end of that. And maybe Ben, with his new role at X Energy, has a specific opinion about that.
Yeah.
But in our role at GAIN, that's what we're looking for, is those places where the national labs and private industry can come together in pre-competitive space and lift up this whole industry. What are the things that we should be doing together as an industry and spending the government dollar on such that Ben preserves his capital to focus on the things that are specific to their design and their business model and how they want to deploy this technology. And I also think it's important to point out here, you don't hear us necessarily just talking about nuclear power. Kristine introduced this, right?
Like,
what's wonderful about this moment is making full use of nuclear energy. And that's different from what we did in the past. There is an opportunity.
Couldn't agree more there. And
as we look at decarbonization, right, we really need to understand what it's going to take to decarbonize. For some parts, it absolutely is electrification. For some parts, we just need to produce heat and steam in a clean way.
wow. Okay. There was like so much awesome stuff there. I definitely want to double click on how you design your fleet. And if you go to a French plant, you take a right, you take a left, everyone is laid out the same way. They're either 900 megawatts or they're 1300. That's it. Doing the materials compatibility reports for the US plants was a nightmare because everyone was different. We also definitely want to get back to like, what is a good use of government money? I think we should definitely flag that one for later. Also the multiple uses, amazing. Would love to get into more like high temperature heat production. Like you said, I think Ben knows a lot about that. But before maybe we move on, I also want to touch on that safety piece with complexity. And I know we've got people on this call who are like, okay, yeah, so we built different types of nuclear plants and they got expensive, but also there were some big headlines, right? That you know, we all, you know, Fukushima, 3 Mile Island, and Chernobyl that are really in the public space, and that's what people think about when they think about nuclear. So I'd love if we could like quickly touch on, hey, how does that affect how we deploy nuclear going forward, and how do you guys view design for safety, et cetera?
And also contextualize what that meant in terms of health and human lives versus inhaling, you know, carbon for the past, 60 years, right? Because I think some things are sensationalists, but putting numbers to it is also important.
Or unfortunately, chemical plant accidents or coal mining accidents, or not.
So I'll share a little bit of my own personal experience, and I'm sure Ben and Kristine remember where they were when they were watching the news about Fukushima as well. So I was an operations director. I was responsible for figuring out where our nuclear staff were across the planet. First of all, like, where were my people related? Did I have anybody in Japan? Okay, that was first and foremost. Second, as I watched the news, and at the time, my son was 18 months old and he's toddling around in front of me as my husband's in nuclear as well. So we're both sitting on the couch, like trying to keep him entertained and digest what we're seeing. It was cold in Japan. Okay, so you had a tsunami and we had displaced a significant number of people. And I could see what was going on in the nuclear power plant, and that was concerning. But I was not worried that they would not be able to handle, knowing the design, knowing what was going on, that would be okay. I became more concerned that we're not talking about the people that were displaced by the tsunami. We were wrapped up in the sensationalist, the explosion at the nuclear power plant. And that's where nuclear, I think with 3 Mile Island, we started to fly under the radar screen, right? We insulated ourselves. We spent a lot of time as an industry only talking to ourselves. And I do believe that was probably our biggest mistake. In going back to France, I'm truly not a French citizen, and I'm not trying to get dual citizenship here, but French citizens understand nuclear power. And so I think this is, and this conversation is the start of, we can't just continue to talk to ourselves about nuclear power. We need everyone to understand how this technology works and not let it be as intimidating and as scary as its history has had in the US.
Well, and if I could just add to that, Kristine, I think that we see that very strongly in the US. if you look at kind of this societal compact and where do people, as Carly said, want to live near a nuclear plant, it is the people who live near them now who are most interested in the levels of acceptance and support are strongest the closer you get to the nuclear power plant itself. So clearly the dialogue has been too insular. If the people who live in the community and know neighbors and family members who work at the plant, they're going to, we I think can safely assume, have a good understanding of the technology as any layperson might have, and their acceptance of it and living near it is quite strong.
So
I really want more tours. Every nuclear plant should get more tours.
they should.
You know,
They
that was
absolutely-
that was actually a really unfortunate thing about 9/11 is that due to the US's revised view of the threat to the country, the security perimeters were fortified and in many cases moved out far enough that the visitor centers at nuclear power plants, some of which were very impressive or are very impressive in the US, then fell within the security perimeter. And so they no longer could have tours or technology demonstration or bring in the hundreds of students that they used to do annually. So that was a real net loss after 9/11.
Yeah, let me just hit a couple of points that I think we've discussed, but maybe just a couple data points. So, if you plot every source of energy along a bar chart, and you look at the number of deaths attributable to that industry, and this is not looking at necessarily even air pollution deaths. That definitely skews things in favor of clean energy technologies. But if you plot that, nuclear is at the lowest possible end of the spectrum. And that's because of the safety culture that has been inculcated coming out of, frankly, the development of the nuclear Navy program and the regulatory approach that the United States has as the highest standard of regulation in the nuclear industry in the world. And so that is a good story in and of itself. But those deaths are unfortunately typically things that happen in standard scenarios in any large industrial plant, right? So there was a set of accidents that happened, I believe, at a reactor in Arkansas where a crane dropped payload and killed an employee. That was a death that was attributable to nuclear. 3 Mile Island was the largest and most, impactful, devastating nuclear accident in the commercial nuclear industry history of the United States, and there were 0 attributable deaths. So that, just to put that in some level of scale, our worst accident did not cause any deaths from radiation exposure, which is really not well understood by people. Okay, so fast forward to today and what we're doing. I'll give you an example of a reactor technology that my company's working on, but it's similar for a lot of these technologies. One of the benefits, and Carly got into this, I think, a little bit earlier, to these other technologies is that you may not have to have the types of defense in depth safety standards that you do for today's commercial nuclear reactors, right? So the biggest threat to a nuclear power plant is to lose your coolant so that the fuel itself gets too hot and there's not a way to pull the heat away from that fuel. And ultimately, that's what we call a meltdown, where the fuel itself actually goes beyond its structural integrity point in temperature, and it begins to melt. And then you have a kind of a nasty mess to clean up. And there can be other sort of fallout incidents coming beyond that, like steam explosions or hydrogen explosions, which hydrogen can be produced in that type of accident scenario. Today's reactor technologies that we're kind of talking about, these advanced reactor technologies, often are meltdown proof. So an example of that is the reactor that the company I work for is developing. It has a fuel that's called TRISO fuel. Our proprietary brand is TRISO X. The idea behind TRISO fuel is you end up with a really small pellet of fuel. It looks like about half the size of a BB. And you take that small amount of uranium and you coat it in 4 layers of really sort of impressive ceramics. Some of it is just carbon. And so you have a carbon buffer layer, and then you have something called silicon carbide. And silicon carbide, for all those in the tech world, you may have come across this for all kinds of really cool microelectronic devices that are based on silicon carbide. Things that are cool about it, when you compare silicon carbide to silicon, you can run it up at a lot higher temperatures. If you have a single crystalline structure, you can make really cool electronic devices that operate at high temps when, your computer, when you work on it in the sun and in your car, shuts off and says, I'm overheating. So that's an exciting application of silicon carbide. In this case, we're not talking about a single crystalline structure like that. We're using it as a ceramic for its actual structure and heat transportation properties, right? So you have this little pellet. That pellet can survive temperatures way beyond 1800 degrees Celsius, which is really, really hot. And then the pellet gets packed into a ball, and that sits inside of the reactor. It looks like a gumball machine, and you flow your coolant through. So even in the worst possible scenario, you lose all of your coolant. There's no more helium to help extract the heat from those balls. The physics of the reactor does not allow the reactor to ever get to a temperature where it crosses the threshold for the meltdown temperature of silicon carbide. So for our triso particles, they actually cannot melt physically. And if you start with that, with the fuel as a case in point, it changes everything else about your economics. So we're talking about it for the perspective of safety, but really what that means is you use safety to enable a much better economic case for your reactor going forward. That means you can eliminate things like backup safety systems, like redundant pumps. You don't actually need as many components in the reactor to begin with. So, we're conceptually looking at about 1/10 the number of components of the current reactor. And as you get rid of complexity in the design, you start to get rid of those things that cause nuclear to get more expensive over time. Those things where you slap on new safety features, new extra stuff that make it more and more safe, which is great, but also add more and more cost. So, Kristine.
But then I think we should also talk about, taking a look at not writing our own specifications again, right? Really looking at bringing in commercial products and only declaring things safety related when they need to be safety related, which will bring down the cost of our components. It will make us able to manufacture them quickly. I can remember one of my first jobs was to order some hydrogen for some work that liquid hydrogen for some work we were doing at Palo Verde. And I had to write a specific spec. I had a nuclear spec to get a tank of hydrogen, right? I mean, I mean, it was fun. I mean, I was a young engineer and it was fun to do. And we got to ship, I think we had eight tanks of these things that went out there. I mean, that was great, but looking back on it, how silly, right? I mean, yeah. So I think that's also, I think it's that thinking that we're seeing creep in, and Kristine might talk about the transformation that's also going on within the commission and the NRC staff about really focusing on what needs that nuclear unique perspective and what can we accept from a commercial basis that'll make us more efficient.
So jumping in here, so I want to kind of zoom out a little bit because we've moved into like the what's different now, which I really like. So the two buckets we've talked about is Ben talked about safety, right? Where putting safety in the design versus in the thing that's surrounding the design is something that makes sense from an economic perspective. From a safety perspective, we do need to do a lot of education about this, right? And I think that's a huge part of this is just education and information. So we talked about that. We've started talking about the cost structure of making these things smaller, not making everything so bespoke, so you can add some economies of scale to this. So that's also kind of a big component of what's changed. But one thing I want to talk about with the audience, just so we have a baseline of what we're talking about, is why won't wind and solar save us, right? What is it about nuclear power that we're excited about in terms of adding it to our toolkit, right? It's not going to be a silver bullet, but what does nuclear power do, especially fission, do right now in the decarbonization strategy that's unique? And maybe that's a good place to talk about other uses than just electrification.
Well, I'll kind of start us off at a very high level, if I may. Well, back when we used to work in offices with printers, I was a fan of printing things out because of my nearsightedness, but I could, so now I'll just say that you could figuratively have quite a high stack of very, very credible multi-year studies that model the energy system of the US lay it against the decarbonization goals that states have put out there. And that this is an important development of, I'd say, the last 5 years. Individual large utilities in the United States are saying that, by 2030, I want to be to this level. By 2050, I want to have a net zero system. But the most recent of these just came out last month by Princeton. I think it was 2 years worth of extremely esteemed people from Princeton and beyond, who looked at a kind of a fine mesh modeling of the United States energy system. They're very strongly wanted to be technology agnostic in terms of, but they looked at something, what are the chunks we need to provide the energy that we need, and also to electrify other parts of our economy, like transportation, that are not as deeply electrified right now. And then we need to get that electricity from clean technologies. So even with a kind of a technology, they didn't want to advocate for it, but they said, you know what, we need a category called firm, and it needs to be clean. So this was a learning to me that this is now the new euphemism for things like a little bit of geothermal, some hydro, storage, and there's a lot of investment in that going on, appropriately so. But when they ran an optimization algorithm on it, so this again is, I think, one of the most recent reports, and they've been building on each other over the course of the last 15 years, and they're building on the fidelity of the modeling and the computing complexity of this. But the optimized case came out with 250 new 1 gigawatt reactors needed in the United States, or approximately 4,000 small modular reactors by 2050. So these are not dogmatic theologists in advance of nuclear. They wanted to be technology neutral. The optimization algorithm pointed it amongst the firm category, which you need because people want power when they want it. So that was where nuclear landed. And this is, again, not theologists, and it's not people marketing nuclear.
Right. And the idea here is we're not going to get fusion up and running to that scale in that time period. At least a lot of people don't believe that. So fission is kind of the way to go in a certain respect.
They were clear that one of their assumptions was that they didn't want to include in the mix things like fusion. Not that they were taking a view against it, but they wanted things that we had a good sense today of their deployability at what scale.
So I think folks, if you take, like you said, take a step back and you look at the whole system, it's not just necessarily about power generation. It's about how we're going to be using energy and where does that come from. And when you start to think about that, and especially as I've been thinking about that, we have a lot to build. I mean, when you really think about transitioning to a clean energy economy, we have a lot to build. And so from my perspective, I've kind of looked at the transmission system in terms of siting. If you've never looked at what it takes to site a transmission line, that's going to be the long tentpole. So from a preservation perspective, I start to come at it, and I think everybody kind of comes at it a little bit differently, but do you start to come at it of, okay, I want to make the most of that infrastructure I already have, and then deploy technologies as well to that. There's a tipping point associated with this. There's an optimization that I think we all, and scenario planning that we all need to get used to. We're going to be doing a variety of different scenarios to meet these goals going forward. Just to put a plug, because I'm not selling a book, but I am selling an app. No, we're not selling it. It's for free. Gain did look at this, and for people that want to do the math for themselves, right? If you want to look at your state, or if you want to look at the United States, and you want to tailor demand, and you want to do a lot on energy efficiency, you can do that in our calculator, but you also have to figure out how you're going to supply power and do that and meet your carbon emission goals. And I think when you start to do simplified calculations like that, you can do the math for yourself and figure out what that tipping point is. There is a tipping point with wind and solar where it becomes too expensive, whether that's in building or in land use and those types of things. So there's and optimization and thinking about those metrics, will we measure our energy futures based on the lowest cost of electricity, or are we going to measure it on things like greatest net benefit? Are we going to start to look at cross-sector benefits and look at a holistic energy system? We really need to get out of our silos, is my personal opinion.
So
Kristine,
what can I give one minor
Please.
thing? Just as way of background, as you're looking at these different technologies, underneath the stories that you just heard from both Kristine's, the question on why do you need this firm capacity or why nuclear? There are the pithy statements like, the wind doesn't always blow or the sun doesn't always shine, which people like to throw out there. That's true. But what's sort of underneath that fundamentally is the idea that the intermittency of those renewable sources makes them roughly on the order of about 30% available compared to the nameplate capacity that they offer. So sometimes it's a little higher than that, which is great. Sometimes it's a little lower, depends on where you deploy these technologies. Today's nuclear reactor fleet operates at over a 90% availability. It's around 93% available. So if you just do the math on megawatts, to generate the same amount of power, you need to have 3 times the amount of megawatts available, roughly speaking, for your wind plant or solar plant compared to the nuclear plant, because it will only operate a third of the time that the nuclear plant operates. And then if you want to be able to make that dispatchable, there's certainly a lot of interesting technology challenges we're grappling with on the energy storage side that hopefully will get us to the place that you can have more seasonal storage, more longer duration storage, but you're adding that cost on top of the deployment of the renewables. So what you're really saying is for a 1,000 megawatt nuclear plant, the equivalent would be roughly 3,000 megawatts of wind or solar plus the energy storage built on top of it. And that may or may not get you the flexibility that you want to be able to dispatch that at the times you want. So one of the cool things about the new fleet of nuclear reactor technologies that we hope to deploy is that they may be able to follow renewables and load ramp, kind of similar to what we do with natural gas today. Many of you probably are aware that a lot of natural gas sits idle in California right now at an idling level. That's part of the carbon emissions in California come from natural gas plants that are there and available only to flip on when they need to back up natural gas. So we're looking at a potential deployment of nuclear to fit into that kind of gap. And then also what my two fellow colleagues have said is that, there's this greater need, this much larger need. If you're looking at electrifying vehicles, if you're looking at getting into the industrial heat side of things, that's roughly the other 2/3 of the carbon emissions in the US. You've got some for agriculture or other purposes, but really, you can roughly ballpark it as like 1/3 of US emissions comes from electricity, 1/3 comes from industrial applications, and 1/3 comes from electric vehicles. So if you electrify or decarbonize all of that, you need roughly 3 times the amount of power production you have today, or equivalent heat production from clean energy sources. So nuclear can touch all of those, which is really exciting, which means that its market opportunities will start to look much more expansive going forward in the decade or two coming.
Okay, that was a great ad. Thanks, Ben. And I'm torn because I really want us to touch on nuclear waste, because I know that's something that's part of this picture too that people have feelings about we can't ignore, and we have questions coming in that I want to get to. So if we could quickly go to how should people think about nuclear waste with these new plants, and then we'll do some Q&A.
Can I give you the 30-second version?
Please.
Nuclear industry is the only industry in the world that's required to account for every single molecule of waste that we create, right? And that's not true anywhere else. And so we actually know where all that waste is as an industry, which is exciting. And it's not that much waste. So it's an important problem. I've got to tell you, it's a political problem that we haven't gotten to the bottom of, and I'm sure my colleagues have a lot of thoughts on it. But to quantify that amount of waste, all of the power that you use in your entire life, if generated by nuclear power, would fit into one soda can. That's your waste. That's your radioactive waste stream for your entire life cycle of waste, compared to all the other things that you do in your life. You'd imagine how those would fit with fossil generation or renewable generation.
So
And
what I'm excited about, So what I'm excited about with the next fleet is I think today's waste is going to be tomorrow's input. Recycling is a real thing. You asked for it to be quick, so that's all.
That was perfect. Yeah.
And I'll do just a little lightning round here as well. Ben was mentioning that the technologies today are designing in the safety, and Gaetano mentioned that as well. I want to mention, because non-proliferation has not come up, that designers today are also looking to have what they call safeguards by design, meaning, if we can have a lot of clean nuclear around the world, but the end result is that it's a more dangerous world. Nobody in the new technology space is content with that, I can tell you. So they actually want to front end load all the considerations about diversion of material. So they're doing it with safety. They're doing it with what they call safeguards so that we don't have the proliferation, but they're also doing it about waste, because they're keenly aware of society's view about what you talked about. And so they are setting the stretch goal for themselves of wringing so much more of real energy out of the materials that go in. And as Kristine has said, perhaps looking at the inefficiently used spent fuel that exists around the world today, there is still so much usable energy in there that the young people I talk to in the nuclear innovation companies are really motivated by the waste issue, and they want to overachieve by saying, not only will I get more energy out of what I put in, I'll generate less waste, but I think I could use some of this stuff that's lying around and perhaps generate energy from it.
I think that's a good spot to move to some questions, and because I do want to leave a last prompt toward the end around, okay, great, we're all in agreement that this is the future. What do we need to do to actually get there? So before that, let's go to some questions. One question is around, this is a very specific one, I'll read it. The natrium reactor being proposed in Wyoming has been met with opposition from those concerned with sodium coolant. Are the panelists familiar with these claims? And if so, how dangerous is a sodium cooled reactor compared to the other options available?
Well, I'll jump in, and I do serve on the board of TerraPower, and I am no way as credentialed as the many brilliant technology people working on this question, but sodium is something that it plays a role, and it can really be beneficial in these new technologies. We certainly know how to handle intensely corrosive materials and things like that. So we are using what we've learned in the past about harnessing sodium technologies and doing things like, appropriately encapsulating it and other things that are, but there are benefits to using sodium. And I think the notion that there is some dealing with hazardous materials in a productive thing like generating that much energy, the folks are up to the task of doing that, and have learned from historical experiences with sodium, which are limited in nuclear applications.
Okay. And just to summarize there, sodium, molten sodium, what are the hazards? Is this something that gets into the air, into the water? What should people be concerned about versus what is, maybe we could just put a little bit more color on that. Part of this is that sodium is not like water, does not boil, right? Which is
right. So I think the challenge, right, from a materials and a chemistry perspective is you create a corrosive environment. So what is the containment associated for that environment? What materials do we need? Do we need to invent those materials? What pressures do they need to be operating at? Those types of things. Physics do play in your favor in a molten salt, in that the nuclear reaction will automatically shut down, right? So there's a benefit associated with using it as well that gives you that walk away safe that we're looking for in these new reactors. We've gone from active safety systems to the small modular reactors of passive safety systems to potentially what Ben said earlier, meltdown proof or walk away safe, right? I mean, that's the dream, right? That is reaching those things. So to me, it's around, not to say mundane, but I would say non-nuclear issues that can be solved. It's not a nuclear issue associated with molten salt. It's really in the chemistry and the material space that people face in aggressive environments in other industries as well.
okay. Thank you. And I think
Um,
that actually leads into, maybe Gaetano, we're probably going
no,
the
no,
same
no, go
place,
ahead. Go
but,
ahead. Go for it.
Is the US training enough skilled people to manage new tech deployment in nuclear is another question from the audience. So enough, how are we training people to deploy this new technology?
I'll start. No, it's the short answer. I mean,
I agree.
yes, we are.
Right.
Right? We are more so today than we have been for a long time. But right now, if you look across the industry, we had a huge bubble that was created in the early days of the nuclear industry when it was an awesome sounding job and career, and when people were kind of really excited about going into the nuclear sector, going to nuclear grad school, and then eventually that workforce was hitting its sort of twilight, and the U.S. jumped in with some new scholarship and fellowship programs, which were very beneficial to bring new PhDs, new masters, new undergraduate degrees in nuclear energy to the table. And a lot of those people are the folks that are fueling the rise of these new companies, right? There are a lot of young folks in the entrepreneurial world in advanced nuclear reactor companies, and there are a lot of folks from their mid-career to their late career as well. It's a very dynamic time, but we still have a lot to do, because if we're going to actually build out the nuclear industry to be any larger than it is today, you're going to have to fill those jobs. And to be clear, not every job at a nuclear reactor is a nuclear engineer, right? We're talking about skilled labor to build these plants and maintain them. We're talking about electrical engineers, mechanical engineers, process engineers, people with business backgrounds. But you're applying that to the nuclear world, so you got to know something about it. The other thing that's kind of important to note is that globally we're talking about building out a lot more reactors, and globally the U.S. is still considered the number one place for nuclear education in the world. We train many of the best and the brightest from around the world to go back to their countries and help to start their reactor programs. If there's going to be a large build out of reactors across the world, especially in countries that today don't have that type of that type of industry existing or a regulator existing, those are jobs that need to get created and filled, and that will have to happen with a lot more people getting trained. Last thing to mention on that is today a lot of our industry is filled with people who are trained by the Navy, and the nuclear Navy in the U.S. is a great trainer. It's a great educator on nuclear power, and one of the things that's important as we look at the future of nuclear, part of staying in front of the technology race in leading in nuclear technology is what the drawbacks and benefits are to our national security profile, and what we do for naval reactors is extremely important, because if you volunteer to get on a submarine for 6 months at a time and not come up and see air for that long period of time while working on a nuclear reactor, you're only doing that for a handful of reasons, and at least one of those frequently is that the job prospects afterwards are phenomenal. And if the nuclear industry goes away in the U.S., there's very low incentive for people to volunteer for that type of job, which helps keep us safe. So,
thanks, Ben. Sorry, just because we're almost out of time, so I wanted to just give us time to wrap up a little bit. A couple of just quick ideas that we didn't get through is on the small modular reactor side, making smaller reactors means that they can be useful in multiple places, and you don't have to buy a huge thing. You can start small and then modularly scale, which is great. That's kind of one thing that we didn't cover that I wanted our audience to understand. They're safer, right? Because they are smaller. So in a worst case scenario, the downstream consequences are not as big. And by making them smaller and all look the same, you get to mass produce components, right? So those are some of the things that I wanted to make sure that at least we mentioned. One last question is around the regulatory environment, and I want to have that question be the lead off to our final thoughts on how do we actually make this nuclear fission a dream a reality. So curious what the panelists' thoughts are on the regulatory environment. Is there effort to reduce the licensing hurdles without compromising safety? I've worked in the nuclear industry for 15 years and have seen only slow progress toward actual construction of advanced new reactor types because of lengthy and difficult regulatory reviews. So answering that question, but the prompt is, what can we do to actually make this a reality in terms of building these nuclear fission reactors? That's my last question to each panelist. I'm going to start with Kristine S., and then we can do a quick round robin.
Well, it's a little bit like the workforce issue, right? I mean, regulatory systems build up over time and become sophisticated around the technology that's being regulated. So in the United States, the Nuclear Regulatory Commission clearly understands that it will soon be and is now beginning to confront technologies very different than what it grew its whole regulatory system up around. We see this in struggles today to regulate the internet under antiquated telecommunications laws. So sometimes there's an imperfect fit, but I think the regulator also can't be ready ahead of the technology developers. It's the same thing with the workforce. You don't want to have the workforce you would need to deploy 100 new reactors ready now. They want to get a job as soon as you train them. So what you need to be sure is that systems are proceeding apace along with the technology. Now, the thing, and this is kind of my summation remark, is that nuclear has a lot of process, a lot of bureaucracy, and a very heavy government footprint. It is the only technology that I can think of where once you build it and it's perfect, you have to have government permission to get the thing you need to power it up. So in order to own and take title to nuclear materials in the United States, you have to have a deep and rich regulatory relationship with the United States government. So that is unique. I think what government needs to be focusing on and is focusing on is, are we bringing that structure along? It can't get ahead of the technology, but is it right behind so that the systems will be ready? There is a lot of focus on that, would be my answer. And I'll turn it over to my colleagues for thoughts or differences on that.
So I'll jump in. Different, like Kristine started to lead into, different from commercializing other technologies. Nuclear will have a relationship. Commercializing this technology, you will have a relationship with the government. I'm here to tell you, call GAIN, we will help you find the right relationship with the government, because we are here to take all that we've learned within the national lab systems and help companies like Ben's company be successful in their quest. To me, the value of what the government can do here is to help make sure that these technologies make it to market. That's how we spend the government dollar, is ensuring that we're working towards commercialization, that we're addressing questions. On the regulatory process, what I'm happy to see is that we're moving away from deterministic answers and really looking at the real risk associated with these technologies. And that is allowing us to simplify designs as well. All right, Ben.
Great. I'll comment, maybe pivot slightly, because I think the regulator is focusing on the right, direction to head, and there's work to be done there. But this began under Kristine Svinicki's leadership. It's continuing on today, which is exciting, and I think Kristine King framed it well in terms of what the government can do. There are programs today that exist on the government side that didn't exist 5 years ago. And that's really exciting because they're focused on public-private partnerships and commercialization of technologies. The company I work for is a beneficiary of that. But I had mentioned earlier that I spent a lot of time in Congress and at the Department of Energy. And what's unique about today is that not only that the government has these programs, but that they're supported so strongly. So the Office of Nuclear Energy's budget about 6 years ago was on the order of $900 million a year. Today, it's $1.6 billion. The president requested $1.8 billion. Congress is going to fund something there. Congress right now is looking at an infrastructure package, which may include nuclear. First time, really in that way that's been included, both for the current fleet, but also for a couple of demonstration reactors like what we're doing at X Energy. The renewed focus is on bipartisan support. It's about the economic opportunity, it's about the decarbonization challenge, and it's about the national security implications for nuclear. So what's exciting about that is we're having this conversation today with a company, a group of people, investors that are interested in these types of deep technologies. That's not happening elsewhere in the world, right? A lot of countries have a nationalized top-down approach to technology development. They push it to market. Today, we're seeing the market pull, which is great. And that's why you have a whole host of advanced nuclear companies that are trying to get there. We're partnering with the government to try to get through those final hurdles, over the final hurdles across the threshold. and get to market. And because of the diversity of entrepreneurs in the US, we're going to be successful, which I think is really exciting. So.
Was
Right on
I don't think I
time.
can add
You
anything
landed.
to that
You
anyway.
landed
So
us.
that that was perfect. Again, like, thank you all so much for sharing your time and your expertise and your perspectives here. This has been wonderful. I know we're seeing some thanks pop up in the chat as well. So I hope everyone has a wonderful rest of their afternoon. Kristine King said Gain is here. Really thank everybody for their service and
This is so
yeah,
fun.
just time. So
Thank you.
Great. Thanks,
Until next time.
everyone.
All
Yeah.
right.
Thank you.
Thanks.
Bye.